everybody use the default? And it works? You said it?
Yes.
Good. But it doesn't matter. So if you use the default, fine. It just means that the JVM team did a good job, right? So you should at least have some ideas about garbage collection because it has an impact on your application performance, the responsiveness, and also the system requirements. So that means memory usage, CPU usage, right? So this is, garbage collection has a big impact on these parameters. So you should know something about it. And to give you a little refreshment how it works in the JVM. So in the JVM we have threads. And on each thread, there is a so-called stack. And in that stack, we have stack frames. And now all the people will come. Okay, we wait a second, because it's a lot of people coming. Hurry up! Come on! You missed the most important part. All right. Okay, so we have, like I said, we have threads, and for each thread we have a stack, and on the stack we store so-called stack frames. With each method that will be called, there's a new stack frame on that stack. And in that stack frame we store primitives and references, right? And this grows and shrinks dynamically, so we don't have to do garbage collection here. It's thread safe, it's all good. Then we have the heap, and in the heap we store the actual objects, right? So there we use all the memory. This is not thread safe, this is shared access, and we have to do garbage collection in this area. And then there is the so-called meter space, and the meter space, to make it short, because we don't really talk about the meter space, contains constant pool, class meter data, and in principle everything the JVM needs to run classes, right? But we don't focus on the meter space, we just focus on the two things on the left side. And you probably saw stack overflow. That's because your stack on the thread just wasn't enough memory, and you probably know out of memory exception which happens on the heap, right? So these are the two exceptions that we have that are memory related. All right, to give you some idea how it works in code, and everything I showed you is super simplified. It's way more complex, but you should get an idea, right? That's the main intention here. So we start with a record or class of type person. And I created 4 instances of that, and it just has one method, the toString, returns the name. And then I have a list object that also has these 4 objects in there, right? So this is my code, and the stack frame is this one. So we have the 4 references for the person and the reference for the list, okay? And now, if we take a look at the heap, then in the heap we have the actual objects for each of these persons and also for the list. And then we have references that pointing from the stack frame into the heap. So we can follow this, right? And then that means all these objects in the heap are reachable. We can reach them from the stack frames, okay? From this specific stack frame here. So, the stack frame, you will also find if you read something about garbage collection, is often called the root. The garbage collection roots, these are the stack frames. Because they're the references, they're pointing into the heap and they give us some kind of a path we can follow to find the objects in the heap. And now in this case, everything's reachable, that's fine. If I now set the person 1 to null, then you would think it's gone. It will be garbage, but it's not, right? Because you see, in the list object still has an internal reference to this object. So the object is still on the heap, and you still can get the value of this object. And often junior developers forget about that. So they think, oh, I set it to null, it will be garbage collected. No, it's not. Probably somehow it ends up in whatever collection, and it's still referenced on the heap. So it's still available, okay? So this is still reachable. If I now set the list to null, it's gone. And then I can only reach these 3 objects, right, in the heap. The rest, that means the person P1 object and the list object, is more or less garbage. So, how to get rid of it? Garbage collection. That's the idea, okay? So, I hope you could follow this one because this is the basic why we need garbage collection. To give you an idea, garbage collection is a form of automatic memory management. And who did C here in the audience? Okay, the C people love the malloc and free, right? So because then it's up to you to do all this stuff. And in the JVM, we don't have to. And there are other ways of doing it. There's not only garbage collection, there's also automatic reference counting. That's, for example, used in Swift. They use this one. It's more or less same functionality, different approach. Okay? Then the idea is to identify and reclaim not longer used memory. Remember the P1 and the list, when I set it to null, it's sitting still in the heap and it takes the memory away. So I can't use that memory. So I have to somehow find these dead things and clean it up. This is the idea. And everything should happen very efficiently because that takes some time. But in the end, the most important thing is you shouldn't take care about it, right? And for those that didn't, that came a little bit later, I asked before who's setting the garbage collector manually for its production environment, and just one person said he does, which is not a bad thing. But that means you usually don't care about garbage collection. You write your code and you assume it runs, right? And then it works and you're happy. So to give you a little bit more insights, if we talk about precise collectors and just take it as granted in the JVM, all collectors are precise, then we have different phases, right? And the first phase is tracing. That means we have to identify all the live objects that are in the heap. So that means following from the stack frames, the roots, into the heap, all the references to find all the objects that we can reach and then mark them as live, right? This is tracing. And then we have freeing. And freeing is not for free. And I mean that literally like I say it. Because we can't find the live objects, we can't find the dead objects, right? Because the dead objects just simply are not referenced anymore. They are on the heap, but we can't see them. So if we would like to find them, I will show you what we need to do. And then there is compaction. Compaction, if some people might be old enough to remember Windows 3.11, there was something called disk defragmentation. And people who remember this, yeah, I know. This is where we need compaction, and I will show you why it's needed. Who knows what stop the world means? Just a few? It's no problem. That's why I'm explaining it. So because that was one of the reasons why we have lots of different garbage collectors in the JVM, to solve this problem. And the problem is, if we would like to clean up the heap, we have all these objects sitting there, right? You can imagine it's hard if the application allocates new memory and at the same time we would like to clean it up. So that means what we have to do is, we have the application threads running. At some point we would like to do garbage collection. We trigger a save point signal, and then all the application threads will stop in a safe position, right? So that means they are safe, and that's the reason why this is called the JVM save point. At that moment, no application thread is accessing the memory anymore. It's stopping the world, because from the outside, your application looks like dead. Nothing happens, right? And then, garbage collection threads will start collecting all the garbage. Once this is done, we can restart the application threads and continue with the application. And this orange area in the middle, that's the stop the world pause. And it can be, in worst case, up to 10 seconds or longer, depends. And that means for 10 seconds your application will just don't react. It looks like a computer hangs because you can't see anything, okay? And that's the reason why we have different garbage collectors, to make that as short as possible, okay? So that's, if I talk about stop the world, this is the amount of time, the orange area, that's what I'm talking about. All right, that leads me to collectors, and I don't mean the garbage collectors in the JVM, I mean collector principles. Because we have different ones. We have, first of all, a non-moving collector, also called mark and sweep. Who knows that? Or heard about it? Probably most of you heard it once in your life, in a university or somewhere. And let me try to give you an idea. So this should be the heap. The gray cells that you see, this is the memory cells. And if they are gray, they are free, right? I can allocate. If they are blue, they are allocated, that means they are referenced from the stack frames. If they are purple, that means they are dead. So there's no reference pointing to them, they're just sitting there and consuming memory, okay? Then they could have this little red square in the upper left corner. That means the garbage collector found it and marked it as live. I said, okay, I found this object, it's live, I can reach it, okay? If it has a number inside, that means not all the objects will die, right? Or we talk about dead objects, so they will die, okay? Then they are purple, but not all objects will die, they will survive the garbage collection cycle, and for each surviving, they get an increase of this number, right? This is not important for this collector, but for other collectors it is. So let's take a look. So we start allocating memory, and you see objects die young, that's a fact. And we fill up the heap, it's nice because we can allocate freely, everything is free up front. Once we reach the end, we have to stop the world. Now it's stop the world, mark the objects, remove the rest, unmark, continue. Now we do that again, and you see now it's not that nice anymore, right? Because now we have to find free spaces. In this example, pretty simple, every object is one cell. In reality, we have, for example, you would need something like 10 cells, continuous, which is hard to find, right? If we can't find it, out of memory exception, right? And this is the problem with this collector. It's non-moving, which is nice, so we don't have to move stuff around, but we have this cluttered up heap, right? So it's fragmented. And that leads to the problem that we can't allocate fast. And we would like to allocate fast, because the faster we can allocate memory, the faster the application runs, okay? So this is the drawback. So we have the advantage, we don't have to move stuff, because moving things around means we have to update the references that are pointing to this cell. If I take a cell and move it to something else, the data, then I have to update the reference from the stack frame to point to the right position, right? And to come back to this, freeing is not for free. I find the live objects by just following the references, then I can mark it. The dead objects I can't find. I have to go through each memory cell and check, is it used, is it not used, is it dead? And then so I can find the dead ones. You can imagine, the bigger the heap, the longer it takes, right? So freeing is not for free with this collector. Fragmentation is the biggest problem. But still, it's not a bad collector. Leads me to moving collectors. Right? And we have two different ones. We have the compacting collector and the copy collector. So let's start with mark and compact. This is used in the JVM, in some of the garbage collectors. And you will see it's pretty much the same. Now, instead of just mark everything and remove it, we do mark, remove the dead ones, and then we compact everything to the upper left corner here. Just to give you an idea, okay? And you will see, when I stop the world, I don't do it at the very end. I leave some space, because when I need to copy things around to compact, I need some additional space to be able to copy things, like a temporary place, right? So I can't really fill it up completely. So let's take a look at that one. Looks pretty much the same. We allocate memory, objects will die because the references are gone. And once we read, I think it's not the last column, but now we will stop the world, mark, remove, compact, continue, right? So this is the idea if we do mark and compact. Again, freeing takes time. If it's a big heap, it takes longer in this case, because we have, again, to go to each of the cells, right? But you see, once it's compacted, allocation is fast, because then nothing is in front of us. The mutator, that's the name of the part that allocates the memory, can always allocate, like, I need 10 cells, just take the next 10, right? So it's called the bump the pointer mechanism, because it just has to bump the pointer to the next 10 cells, and so it's easy to allocate memory, okay? And that's what we are aiming for. So advantage is we can faster allocate. The disadvantage is we have to copy things, we have to move them around. That means updating references, right? Which might take a little bit of time. And we need some headroom. So that means we can't really use the complete memory, because we need some temporary memory at the end for this compacting algorithm. And now you will see another moving collector, and this is a quite nice one. It's called the copy collector. It's mark and copy, and you will see it looks different. This looks like that. So we have two spaces, same size, and they have names like to space and from space. And you see, when I start, I will allocate memory in the orange and the left area. Once this fills up, I stop the world, I mark everything that is live, and then I copy the live objects to the then to space. I will toggle the spaces in between. You will see the colors will change. And then I copy all the live objects to the other side, which is empty. That means it's directly compacted. And then I can just clean up the complete left side, because I know everything in there is garbage. I don't have to check. Right? Here, freeing is more or less for free. Okay, that's the big advantage here. Let's take a look at that. So we start allocating memory. Everything's empty, which is nice because it allocates fast. Once we reach the end, we stop the world, mark the live objects, copy them, and we toggle the spaces. Now mark, toggle, copy, directly compacted, clean the rest, and continue. You see the advantage here, right? So, of course, we have to update the references when we copy the stuff to the new location, but it's compacted, and we can free the former to space completely because we know there's just garbage in there, right? This is very easy. This is even used, this principle is even used in the G1 collector because that's really effective. Okay, that means this one has one problem, more or less, or two. If we have objects that live for the long time, let's say the whole lifespan of your application, then you have to copy this object every time, right? With every garbage collection cycle, and that's a lot. And the other one is we need twice the amount of space for this garbage collector, because if we heap of 1 gigabyte, then we need 2 gigabytes here, right? This is the drawback. Comes with the advantage of automatic compacting, and freeing is easier. All right, so who heard about generational garbage collection? Good, because this is generational mark and compact. And you will see, before we start with that, we have to talk about the weak generational hypothesis. With other words, means most objects die young, which is a fact. And one of the reasons, for example, is best practice. You should create lots of small methods, okay? Because it's easier to maintain and it's easier to understand. But you can imagine, each method you call, there's a new stack frame, putting on the stack. Once you left the method, the stack frame will be removed and we have garbage. Right? So it means lots of small methods means lots of garbage. Right? So this is just one reason. And this is not only for Java, this is for all kinds of languages. So in the y-axis we see the number of objects, where on the x-axis we see the lifetime of the object. So you see we have lots of short-living objects. They die fast, okay? Then we have some objects that live a little bit longer, and just a few objects live for a really long time. If I now take these principles we talked about and try to use them for this kind of behavior, then I create a so-called Eden space, which is the yellow area, and I only allocate memory here. First of all, it's small. That means if I do garbage collection in this area, it's fast because it's a small area. Most of the objects will die young anyway, so that means I only have to copy a few things to the next step. And the next step is a copy collector. The copy collector is for the medium living objects. The reason for that is, once they survived a specific amount of time, so let's say there's a threshold, once they survived, let's say 15 times, I can then promote them to the next area, right? So that means I don't have to copy them all the time because they survived long enough. So that we get rid of this problem that we saw with the copy collector. Okay. So we divide these areas in the so-called young generation, which is the Eden space and the survivor spaces. So you see the copy collector here has survivor spaces, survivor space 1, survivor space 2. And then the blue area is the old generation, okay? And we do a minor collection in the young generation, and we do a major collection in the old generation. That means we have 2 different garbage collection cycles that we run on this heap, okay? And there's also a so-called full collection, that means both major and minor collection. So this is in principle how generational collector works. This is just one example, and of course I have a little demo for that. You will see that I will only allocate memory in the yellow area, in the Eden space. Objects that will survive, I will copy into the survivor space, in the orange one. If this is filled up, I will toggle, and so on, the same stuff that we saw. in my example, if they survive 3 garbage collection cycles, I will promote them into the old generation. I will do this once, and then we will see a fast forward. So I will just really speed it up until the blue area will fill up, because that takes some time. So let's take a look at that. And then you should get an idea how it works. So we allocate memory, objects die young, stop the world, mark, copy them, and then clean, continue, right? And every time you copy means you can just clean up the yellow space, because you know it's only garbage in there, right? So we do that until we have this, we reach the 3 life cycles, or let's say survivor cycles now, and then we promote them into the blue area, the old generation, and now I do fast forward, and you will see there's some kind of a wavefront moving in the blue area, because objects, even in the blue area, will die after some time. So that means once we fill that up, we do stop the world, and then we do mark and compact in the blue area. So now I will slow down. We continue. Once the blue area, and you see it's most of it is garbage now. Now we do that, stop the world, and then mark, compact, and then we copy everything that is still alive in the young generation also to the old one. And then we continue. This is a full collection cycle in this mark and compact collector. And there's one collector that used a similar approach. It looks very similar to this one. We will come to that in a second. I hope you get the idea how it works, right? So it's a quite smart approach to get around all these problems that we saw with the objects die young thesis. Okay. That was the simple part. Now, what about doing that concurrently? So that means the application is allocating memory. We don't stop the world, and we just try to clean it up at the same time. That's the hard part, right? Because concurrency is hard. So if we, and we only take a look at concurrent copying, which is one, there's also concurrent marking, but we don't have the time for that. So if we would like to do concurrent copy, so that means we have the from space, just think about the compaction time, and when you move things to the upper left corner. So this is our object, and we see there are the stack frames, they point to this object, right? They have references, and they point to the header. And now we would like to copy this object to the right side. So if we do stop the world, then we stop the world, easy peasy, copy this stuff to the new location, then we install a so-called forwarding header in the old header, and then we update all the references to the new location. Once we're done with that, we can remove the old object. Keep in mind that for this amount of time, we have to use both memories, right? So both objects take up space. So, and the reason why I mentioned that is that the physical memory that is below that, because we talk about virtual memory here. And this is all baked by physical memory that you have in your machine. This is done by the operating system. And in this case, we can't release the physical memory for the old object until all the references are updated, and then we can remove it, and then we can release the baking physical memory. So that means now we can remove it, and then we remove the stop the world, pause, and continue working. So this is if we do stop the world. So if we do that without doing stop the world, we just say, okay, go for it. Copy the stuff. Okay, nice. We install the forwarding header as we did before. And yeah, both objects are live. That means we didn't stop the world. Application can still access it right now. And that means now one thread can access that one and the other one can access that one. And that's the worst case, because which is the right object here? We don't know. Right? So this is the problem if you do concurrent copying. So there is one solution, there are multiple, but we just take a look at one. And that's the so-called Brooks pointer. This is also used in the Shenandoah collector. So if we use the Brooks pointer, then what we do is we install an additional pointer, a forwarding pointer, on top of the object header. And this one just points to the object header itself, so it doesn't make sense at all. If you see that, then okay, what's the point? It gets interesting once we copy the object, and this is an atomic operation now, which is very fast. And then this forwarding pointer points again to the object itself. So we have a copy, it's not reachable at the moment. And now the interesting part is that we install a forwarding header here. We then point the left one to the right one, and then we release the atomic lock. And at that time, we can update reference, and it doesn't matter which thread accesses which one, because it will always access the right object in this case, right? So this is if you use a Brooks pointer. I know it's complex, you don't have to remember that. Just if you stumble upon Brooks pointer, this is for concurrent copying, and this is used in the JVM. It's just this smart ideas on how to solve these concurrent problems. And concurrent marking is a different story. But we won't go through that. And again, we have to keep the old object until all the references are updated, because this contains the forwarding pointer, right? So we need that for updating the references. And then we can remove it, and then we can continue. Okay, this is concurrent copying, and this should be enough for the hard part. So now let's take a look at the stuff that is available in the JVM. So you know it should have a better understanding. If we start with the serial collector, which is the oldest one in the JVM, then this is, I have some kind of a data sheet for that, and you will see the availability, if it's parallel or concurrent, generational, the heap size, and you see the heap size small to medium. So if you ask me what means small to medium, it's a little bit wishy-washy, right? The reason is, if you would ask me 10 years ago, it would be a totally different answer. So it doesn't make sense to tell you, oh, it's 1 gigabyte is small, because it could be 2 tomorrow, right? So it depends. In this case, let's say 4 gigabyte is medium, okay? But maybe who's working with large heaps? I mean, 64 gigabytes and more. No one? 16 gigabytes. 8? Or is someone has no idea? It can happen. So I guess who's working with microservices here? Okay, so usually you have small heaps like maybe 2 gigabytes. Yeah? Someone with 1.5 gigabytes maybe? Or 1? Because this is now very interesting. You will see why. Because you said, most of you don't set a garbage collector, right? Then this one comes into play. Because what happens is, the serial garbage collector will be selected by the JVM automatically if you don't specify a garbage collector, if you only have one CPU, or if you have less than 1.8 gigabytes of RAM. If you don't specify it, you will get this one, right? And I hope you are aware of that, because mostly the problem is people these days, cloud costs are, it's expensive to run something in the cloud, right? So that means cloud cost is a thing. So your manager might come to you and ask, I know we run it with 2 gigabytes, but do we really need them? Can we go slower than, or smaller than that? Yeah, sure, we can run with 1.5 gigabytes. Cool, let's do it. And suddenly you see some pauses, right? Application got stuck. Oh, what's going on? Probably the JVM chose this garbage collector, and you see why it might be a problem. So if we see young generation on the left side and the old generation on the right side, you see we could have multiple threads. Then we stop the world, and then we have one thread that does the garbage collection. And one thread is not really a lot, right? And that might take time. And this is even space. That means we do that lots of times. And in the old generation, which is the blue thing, could be very big. It takes even longer. And you might even have wondered why the blue area was so big compared to the other ones. Let me give you an idea. So, if you have objects that live for a long time, right? That means if you make the old generation big, it takes a long time until you have to do a garbage collection there. And maybe you never have to do it. So, could happen, right? Depends on how long your service runs. That means even if we can get rid of the old generation, which might be really long, like seconds, even in the young generation, which is very often, we just have one thread to do that. And that can take time. So if you have these kind of problems, think about it. Then you have to maybe specify another garbage collector. Because this happens only with the serial one. And the reason for that is that in the past, they decided to, if a machine only has one CPU, it can't be a server. That's a fact. If it has less than 1.8 gigabyte, no server. So then they decided it needs to use serial garbage collector. That's the reason. To overcome that problem, the smart people decided, oh, let's do parallel DC. which is also called the throughput collector, and there's a reason for that. So this one works in parallel, and I will show you where the difference is. Again, it can handle a little bit bigger heap sizes, and the biggest advantage is the throughput is really high. And if we talk about throughput, that's the time we spend in the application versus the time we spend in garbage collection. So that means if we spend most of the time in the application and just a little bit of time in the garbage collection, we have really high throughput. And this is the reason why this is called the throughput collector, because there's no other garbage collector that is as fast as this one when it comes to throughput, okay? So you can switch along with two different switches, and I will explain where the difference is. You see use parallel GC, and there is use parallel old GC. And use old GC doesn't mean it's the old version of the other one. There's a reason, and it's a little bit misleading here. You also see the CPU overhead is a little bit higher than the other one, probably, but it's really subtle difference. This is a really good collector if you don't really have pause time requirements, and I will show you why. And it's good for batch processing, for example, or scientific computing and stuff like that. So, the interesting part is this. If we use parallel GC, the young generation, that's the yellow area, right, and the copy collector, will be used multiple threads to do the garbage collection. If you have lots of threads, you can do a lot of stuff in parallel, so that means the stop the world pause is very small. Problem with this one, once you have to do an old generation, it's the same algorithm that was used for the serial, it's just one thread. And that can lead to the fact that you have super high throughput, and suddenly it stops for 10 seconds. Because old generation, one thread only. And now, then, the parallel old GC comes into play. With this one, they use a parallel approach even for the old generation, and that's what it means. Parallel in the old generation. That's the reason for parallel old GC. Right? So that means if you specify this one, it will also use multiple threads for the old generation. Yes?
Is there a reason why the default is not?
Oh, there's no default. You can choose. So this is just a different, it's more or less the same collector, but it used a different approach for the old generation, and that one came after the other one. So it's just to make it more complex, you know? It's fun. So, especially the name, when you read it, it's like, oh, that's the old version. No, I don't want to use that. Oh, you would like to use that one, if you can, right? So this was the default collector in JDK 5 to 8. So is someone still at 6, 7, or 8 in the audience? Because then this would be the default for you, right? In these days it's G1, but at that time it was the parallel GC. All right. Leads me to CMS, concurrent mark and sweep. And this collector is pretty much, the layout looked pretty much the same to the one that I showed you, the generational mark and sweep. This is very similar. And this is deprecated, and now I have to ask, who's still on JDK 11? No one? Because you can still use it. Everybody that's on 14 or above, sorry, it's gone. So it was removed from the JDK. And the reason for this collector was that the pause time, you saw in the other ones, it was more or less unpredictable. First of all, we don't know when it happens. Second of all, we don't know how long it will take. But with this one, there was some restriction. They said it is shorter than 1 second. That was a start, right? So at least only 1 second. That's okay. If your web shop stops for 1 second, not nice, but still, you can handle it. If it stops for 10, Black Friday, not so good, right? If you, let's say you have a high-speed trading application at the stock exchange and it stops for 10 seconds, that could be very expensive, so you don't want to go there. So 1 second max, that was quite good. In general, that was a quite good collector. The reason why they dropped it, there have been 2 reasons. One reason is that was not compacting. So that means the old generation, there was not mark and compact, it was just mark and sweep. And that means over time, old generation got cluttered and not really nice. That was the one thing. And the other thing was the code was so complex that the developers decided to, nobody really would like to maintain it anymore. That was the reason why they got rid of this collector. And you see, it was already partially concurrent. I don't go through the diagrams, they get more and more complex now. But it could do concurrent marking, so it could mark the life cells at the same time when it was allocating. And also the sweeping, that means the freeing, was partially concurrent. That was also the reason why, I don't know if you saw it, CPU overhead was a little bit higher, because everything you're doing concurrently means you need CPU to do that, right? If you have 100 cores, and you run your application using the parallel GC, that means you have 100 cores for your application. Stop the world, do the garbage collection, 100 cores. Continue using 100 cores, okay? If you use this one, you have maybe 90 cores for the application, you need 10 cores for doing garbage collection concurrently. So that means you see a drop in performance always when you do concurrent garbage collection, that's a fact. Okay, so that means the CPU overhead was a little bit higher than with the parallel GC. It was deprecated in JDK 9 and then removed from JDK 14 onwards, so it's not in the JDK anymore. And that leads me to G1, which is the current default garbage collector. That means all of you that don't set a garbage collector, this is the one that you use. And this is a quite interesting one because this is different from the others. That was the first region-based collector. And you see it looks different here because we have these squares, the bigger ones, and this is a so-called region. And the size of the region depends on the heap size. So it can be, the maximum size can be 32 megabytes of one region. And the regions can look like this. So you have, again, the yellow areas is the Eden space, the Eden regions. Then we have the survivor regions, and we have the old generation, the old regions, and we have humongous regions. Yay, they are so humongous. The reason for that is, if you have an object that is bigger than half of the region size, it will directly become the humongous object, which is more or less an old generation object. You don't move it around, you just keep it where it is. The problem with this one is, even if it just takes a little bit more than half of the region size, it gets the whole region. And sometimes that can lead to problems, because if you handle a lot of big objects in your application, then you might run out of memory just because you have a lot of humongous regions, right? And sometimes that happens. It really depends on the application, but it can happen. Okay, so one advantage, directly you can see it is, the regions are small. Garbage collection in these small regions is fast, because they are all max 32 megabytes, which is not really a lot. Another thing is, this is called garbage first. So you might ask yourself, okay, what does it mean? In my example, we have 6 Eden regions, 6 yellow regions. Once I run out of these 6 regions, I have to shortly stop. And then I take the 2 regions with most of the garbage in there. That means I just have a very few live objects, take them, and copy the live objects into a survivor region. And then I can directly remove the old regions. That's the idea. So we take the objects that have, or the regions that have the most garbage in there, and then take the live objects out of there, put them into a survivor region. And the same goes for the survivor regions, right? So if they run out of space, we take the 2 with the most garbage and make them an old generation region. Let's take a look at that. So, start it. We allocate memory, and you will see it takes some time, and our objects will start to die, as you see. And once we have the 6 regions, then we take the 2 with the most garbage and now promote them into the survivor regions. So in this time it was 2 survivor regions, now we have a 3rd one, and this continues. Because I have 3 survivor regions, so now we will see old generation. And we continue with this. And you see, it's very flexible, because the regions are not bound to the type. It could be a survivor region now, it could be an old generation or old region afterwards. So this is a quite good algorithm, because it handles a lot of small regions, and garbage collection is fast. And this is always because we copy stuff to the survivor regions and we copy stuff to the old regions. The advantage is the former region we can completely wipe out, because we know it's only garbage in there, right? So it makes it a really fast collector. And you see, and we stop it here because it takes forever to end. So this is part of the JDK since JDK 7 update 4. You could enable it in that one, but it became default in JDK 9. So up to JDK 8 it's parallel, and from JDK 9 onwards it's G1, even today, and which is a really great collector. The pause times max should be 200 milliseconds for this collector, which is quite fast. And usually you see 100 milliseconds or down to 50 milliseconds. So it's quite a good collector, quite fast. It has a sweet spot. So the heap size, if it has 16 gigabytes, it has the best performance for 16 gigs of heap. You can go lower, you can go higher, but the sweet spot is 16 gigs. Right? So just to keep that in mind. So if you have a really small heap, maybe serial or parallel might be a better choice. You have to give it a try if you have problems. If not, just keep it going. This is a good garbage collector for all kinds of stuff. It's good for large enterprise systems, for mixed workloads and so on. It is partially concurrent. It's more or less the same as with the CMS that we saw, but it doesn't come with these problems like fragmentation. So this is the diagram. We go through that. It also can do concurrent marking, concurrent freeing, partially, not all the time. Leads me to the next one, epsilon. Who knows epsilon? GC. This is my favorite one because this is a no-collector collector. You can select a garbage collector that doesn't do any garbage collection here. So this is like using cmalloc without free. You just allocate memory until you run out of space. So you might ask yourself, okay, that really makes sense. It makes sense if you would like to test, for example, the performance, the pure performance of parts of your application. Because if the garbage collector doesn't step in, usually if you do benchmarks, you always benchmark with garbage collection and you can't predict when it will happen. If you use this one, there is no garbage collection, right? So that means you can really measure the application performance. The problem is, like I said, if you ever try it, you will see you start the application, usually it directly crashes because it runs out of memory. And then you get an idea how often we do garbage collection in the JVM. So you can also use it for very small services where you exactly know how much memory you really will need. If you know it, then this is the fastest thing you can do because it doesn't do any garbage collection at all. Okay? But yeah, you have to be very careful. You see it already with the switches. Unlock experimental VM options. Right? That means, oh, if you would like to use that, there is something like experimental, so be careful with that one. Shenandoah, who knows that? Someone ever heard about it? Okay. This was developed by Red Hat, and this is the first fully concurrent garbage collector. And it's parallel, it's fully concurrent. The version in JDK 24, which we have since last week, Tuesday, if I'm right, there's also now a generational version of it. Before that, it was the only collector that was non-generational. Remember, if you have generational garbage collection, you can do lots of small garbage collection cycles in the even space, and that makes the whole thing fast. If you don't have generation, it means you always have to use the whole heap. You have to garbage collection on the whole heap, takes long. That means with the generational version, we will probably see huge improvement in performance. This was made for big heaps, 100 gigabyte plus. It will work on small heaps, but it's better if you have bigger heaps. Right? And all the collectors that I will show you now have the same feature. You see the moderate, it's 10 to 20% the overhead, so it's again higher because it's fully concurrent. It means you really need some CPU at the same time doing the garbage collection, right? It's not available in Oracle JDK, so it's available in Oracle OpenJDK. That means in all the OpenJDK builds except in Oracle. Just to let you know, if you would like to use it, you can't. You have a little bit of a reduced throughput. This is because of the concurrency, and they use new concepts like barriers, but I will come to that because, yeah, we still have a couple of minutes left. Now we'll talk about ZGC, the Z garbage collector, which is the latest addition to OpenJDK. And this is, again, we have old and young generation here. We don't have any survival regions and this kind of things, which is also not needed. I won't go into detail in this one. And the reason for that is that sorry for Anna Maria, you have to close your ears, but this is more or less a copy of another connector, so which is exactly the same algorithm, and so it doesn't make sense to go through the same thing again. Again, this is fully concurrent, it's parallel, it is generational since JDK21, and since last week, in JDK24, the non-generational version was removed, so we only have a generational version now, which is good because this is faster. This can be down to 1 millisecond, or this is usually what we see is 1 millisecond of garbage collection process, which is really fast. Yeah, I get a science here, but it's still, it's 15 minutes on the watch there, so I still have some minutes left. This is for highly concurrent applications, right? And low latency applications. So, last one, C4, and everything I say now also applies for ZGC. Right, so C4 was invented by Zero, I think it's 14 years ago, and we don't go into this one. I would like to explain the different phases because that's different from the other collectors, and like I said, this is the same in ZGC. So we have different garbage collection threads. They follow the routes, that's the stack frames, and they find the objects on the heap, and what you see here, the LVB, is what we call the loaded value barrier, and in ZGC is called color pointer, and it's the same thing. So that means it's some code that will be executed every time you access this memory. So we mark, the garbage collector marks all these cells because it finds it, and then suddenly the application thread steps in and says, oh, I would like to allocate memory. So it allocates the memory, it triggers the LVB, the loaded value barrier, or the color pointer, and then it will mark the cell as live. The application thread will do that by using the LVB. And then it will pass this information to the garbage collector. So that means there's no need that the garbage collector has to figure that out on its own, right? So they work hand in hand, the garbage collection thread and the application threads, by using this barrier here. There's unfortunately not enough time to go into detail here, but Another thing is that, remember, the forwarding information in the other collectors was stored in the old object header, right? And we have to keep it in memory as long as possible. Here, we store the forwarding information in an off-heap page. It's not in the old object. That means once we removed all the objects, we can directly release the physical memory below that. Okay, so this is going on, and then the application thread, once it tries to address the old one, it will trigger the LVB and will look up in the lookup table, which is off-heap. So there's no old object needed. Again, this is made for very large heaps. The customer with the biggest heap that we have has 21 terabyte of heap. And this is really, I was shocked when I heard that, because this is just the heap. So, and we have garbage collection processes below 1 milliseconds and 21 terabyte of heap. But believe me, the machines that you need to run that, they love cores and they love memory. So this machine has a huge amount of memory and lots of cores, more than 100 cores. Then you can achieve that. You can't achieve that on a Raspberry Pi. Right? Just to make that clear, the same goes for ZGC. It will work. The best performance you get with lots of CPUs and lots of memory. This is just how this collector is made. That's a diagram, we don't go into that. Just shortly, you have throughput, latency, resource usage. I'm done in a couple of minutes, I promise. But you can't choose all three of them. You can't choose 2 out of 3. So you can have high throughput and low resource usage, but you can't have low latency at the same time. That's important to remember. But it doesn't really help you. I see the question mark in your faces. This might help you more, which is if you don't care about pause times, right? But you care about your resources, then you're on the right side of the diagram. If you say, no, responsiveness is king, I don't care about resources, then you're on the left side. And all the rest is in the middle where you see G1, and this is where all of you are, right? Because most of you said you don't sell it, so that's it. Overview, I will provide the slides so you can look it up. This is just a table that gives you an overview about all of that. And with this I'm done. Thanks for attending. If you have questions, I will be outside. Just come to me and we can talk. That's it. Thank you.